Hi everyone. In this video, we are going to discuss examples based on Cantor's intersection theorem. Okay, so Cantor's intersection theorem and its converse part we have already seen in our previous video. So in this video, we are going to discuss examples based on Cantor's intersection theorem. Okay, so this is our first example. Fn is equal to open interval n comma infinity. Actually, it is a sequence of intervals. Getting? F1 will be, let me show you, F1 1 comma infinity, F2 2 comma infinity, F3 3 comma infinity, and so on. So such sequence of intervals or sequence of sets we have, and we have to check whether the Cantor's intersection theorem is applicable or not. Okay, first we will check it is applicable or not, and after that we have to find intersection of Fn. We have to find the common part, okay, intersection of all these sets Fn. So let us start to discuss. And I should mention the most important thing is in RDU, with a usual distance we have to find the intersection, and with a usual distance we have to check whether Cantor's intersection theorem is applicable or not. Let us recall the statement of Cantor's intersection theorem first. The Cantor's intersection theorem says we should have a sequence of sets, getting, such that each set is non-empty. This is the first condition. The second condition is each Fn is closed. Each set should be a closed set. This is the second condition. Third condition, it should be a decreasing sequence. That means F1 contains F2, F2 contains F3, F3 contains F4, and so on. And the last condition, diameter of Fn must goes to 0 as n tends to infinity. If all these four conditions will satisfy, then only the Cantor's intersection theorem will be applicable. So for this example, we have to check that theorem is applicable or not. That means all these four conditions are satisfying or not. Let us see. Okay. See, this is Fn we have. Let me mention it again. We have Fn is equal to n comma infinity for all n belongs to set of natural number. Okay, so obviously it is a non-empty set. We will check the second condition, the set is closed or not. When we say the set is closed, if its complement is open, let us find its complement. Suppose such R we have set of real line, okay, real numbers, n is somewhere here, so our set is open interval n to infinity. Getting? So its complement will be this part. That means, let me mention, Fn complement is minus infinity to n. Okay, but here we should write a closed interval because here we have a open. N does not belong to this set, so it should be in its complement, right? For all n belongs to set of natural number. But see, it is not an open set. Clearly, Fn complement is not open. The complement is not open, so that's why the set is not closed. Implies Fn is not closed, right? For all n. For all n. That means the second condition is not satisfied. Fn is closed, that is not satisfied. So that's why the Cantor's intersection theorem is not applicable. Let me mention clearly. It is not closed, so therefore Cantor's intersection theorem is not applicable for this sequence of sets Fn. N belongs to set of natural number. Okay, so we got the answer of first question. This Cantor's intersection theorem is applicable or not, so it is not applicable here, right? Okay, so let us move further. After that, what we have to do, we have to find the intersection. Let me clearly mention what we have to find. Okay, let me mention. Now we have to find intersection of Fn. N belongs to set of natural number. Okay, so we have to find the intersection. So what will I do? I will take any arbitrary point from the intersection and we will solve. So we'll get an idea what will be the intersection. So let us take one arbitrary point. Let x belongs to intersection, n belongs to set of natural number. Okay. So x is in intersection, that means x belongs to each set. It means x belongs to Fn for all n belongs to set of natural number, right? Fn, what is my Fn? Fn is n comma infinity, okay, for all n belongs to set of natural number. This is so much important thing we have got, okay. X belongs to open interval n comma infinity. So let me call it as 1. Let us move further. See, I am going to use Archimedean property here. Do you remember Archimedean property? This property says if you have any real number, definitely we can find natural number greater than that. So I am going to use here by Archimedean property. See, this property says there exists a natural number n such that definitely we can find natural number greater than given real number. So here in this case I am going to take the same x. Okay. So let me show the diagram. Suppose this is a real line. X is somewhere here, okay. Natural number n is greater than x, so capital N will be somewhere here, right? Here we have minus infinity, here we have infinity. So obviously that x does not belongs to this interval n comma infinity. Getting? Does not belongs to this interval, since x lies in the left hand side of n and see that interval lies in right hand side of n. So that's why x does not belongs to that interval. But see, we get a contradiction to this statement number 1. Since this statement says x lies in all such open intervals, okay, all such open intervals, this is true for all natural numbers. But here we are getting natural number n for which this is not true. So let me mention, therefore we get contradiction to 1. We get contradiction to 1. So now the question is why we are getting contradiction? Because our assumption is wrong. What we had done, we had taken one point from the intersection, but see, we are getting contradiction. It means it is not possible to select such point, okay. Therefore intersection of Fn, n belongs to set of natural number, does not contain any point. We had taken one point, but we are getting contradiction. That means there is no such point which lies in intersection. It means the intersection is empty set, okay. I am going to mention that thing, just make a screenshot of it. So therefore intersection Fn, n belongs to set of natural number is fine, empty set, okay. So in this way we found out the intersection also. So the first example is over here. Let us go for the second example. Make a screenshot of it. So this is our second example, okay. So here Fn is a sequence of sets which are defined in this way: open interval 0, 1 by. Let me mention, we have Fn is equal to 0, 1 by, okay. So obviously the first question is we have to check whether the Cantor's intersection theorem is applicable or not. But it should satisfy 4 conditions, then only the Cantor's intersection theorem is applicable. So the first condition is each Fn is non-empty. Second, each Fn is closed. This is second condition. Third, it is decreasing sequence. That means F1 contains F2, F2 contains F3, F3 contains F4 and so on. And the fourth condition is diameter of Fn should goes to 0. Diameter of Fn should goes to 0. If given Fn will satisfy all these 4 conditions, then only the Cantor's intersection theorem will be applicable. So let us check all those conditions one by one. Non-empty. Clearly it is non-empty. It's an open interval and starting at 0 ending at 1 by. So obviously there are some points. So the next important condition is it is closed or not. When we say the set is closed, if its complement is open, okay, so what will I do? I will find its complement. Let me show the diagram. At the middle always we have 0, here suppose 1 by n, right? So this open interval we have, open interval. Here we have minus infinity, on that side we have infinity. So what will be its complement? Tell me. Its complement is, so we have to remove this part only from the real line. So we will have minus infinity to 0, close at 0. Since 0 is not included in this set, so we should cover it. Union on that side now, starting at 1 by n, close set, open at infinity. So this is, see, this is the complement of Fn. But see, the complement is not open clearly since closed intervals are there. Clearly, Fn complement is not open. So the complement is not open, so that's why the set is not closed. Therefore, Fn is not closed for all n belongs to set of natural number. Okay. So the second condition is not satisfied. So that's why we can say the Cantor's intersection theorem is not applicable. Let me clearly mention. Therefore, Cantor's intersection theorem is not applicable for this sequence of sets Fn. Okay, so the first part is over. Now in second part we have to find intersection of all these sets Fn. Okay, so let me mention. Now we will find intersection Fn, n belongs to set of natural number. Okay, so we are going to find the intersection now. Let me remove this part. Okay, we will use this space to write. So we have one simple technique to find the intersection. So what will I do? I will take any arbitrary point from the intersection. We will solve and then we will get an idea what will be the intersection. Let x belongs to intersection. Intersection means what? It lies in all sets. So x belongs to Fn for all n natural number. N belongs to set of natural number. Let me put the definition of Fn there. X belongs to open interval 0, 1 by n for all n belongs to set of natural number. Let me draw the diagram so you will get an idea. 0 we have, 1 by n we have. It belongs to this open interval, that means x will be somewhere here, getting x will be somewhere here. So therefore I can write 0 less than x less than 1 by n for all n belongs to set of natural number. So much important thing we have got, let me call it as 2 now. Okay, statement number 2. Again, in this example also I am going to take the help of Archimedean property. That property says if you have any real number, definitely you can find a natural number greater than that. So here also I will do the same. Therefore, by Archimedean property, there exists natural number n such that you can take any real number, positive, negative, doesn't matter, 0, whatever you want, getting. So definitely we can find a natural number greater than that real number. Okay, so this time what I think, I will take real number is 1 by x. 1 by x. No need to worry, x is greater than 0, that means x is non-zero. So if you take reciprocal, it will be safe, getting, since x is non-zero. You can definitely do. See, what will I do? I will take reciprocals of both sides. Let us take reciprocal 1 by x. Inequality will get changed. So I made mistake, getting. If you take reciprocal, this x will be in numerator, inequality will get changed, and n will be in denominator. Let me write properly. 1 by n less than x. See, here we are saying that x is always less than 1 by n, always less than. N is, this is true for all natural numbers, but here we are getting a natural number such that 1 by n is less than x. So we get a contradiction to statement 2. So we get contradiction to 2. Getting? So we get a contradiction because here we are saying 1 by n is greater than x, here we are saying 1 by n is less than x. So we are getting contradiction, means our assumption is wrong. What was our assumption? We had assumed there is some point in intersection. That is wrong. That means there is no any point in intersection. It means the intersection is empty set. Okay. So let me clearly mention here, just make a screenshot of it first. So I have clearly mentioned here, therefore the intersection does not contain any point, right? It means intersection Fn n belongs to set of natural number is an empty set. That's it. Okay. So yes, we got the intersection. So the second example is over here. We will go for the third example. Just make a screenshot of it. So let us discuss this third example. Okay. So in third example also we have to do the same thing, right? This is a given set. We have to check whether the Cantor's intersection theorem is applicable or not, having 4 conditions. First is each Fn is non-empty. Second is Fn is closed. Each set Fn is closed. Third is it is decreasing sequence, right? Fourth is diameter of Fn tends to 0. This is the fourth condition, right? So if all 4 conditions will get satisfied for this sequence of sets, then we can say Cantor's intersection theorem is applicable, right? See, we will check all these conditions one by one. Fn is non-empty. Clearly there are some elements, so it's non-empty. I am little bit doubtful about the last condition, so I will directly jump to the last condition and I will check whether it is satisfying or not. See, what will I do? Consider. We have to find diameter, but see, we have an interval, so that's why I will find its length. So I'm sure you are familiar with the formula. Length of open interval AB is B minus A. This is a formula which we have already studied in our schools. See, same formula I'm going to use, the last point minus first point. So the last point is 2 plus 1 by n minus the first point is 1 minus 1 by n. So 2 plus 1 by n, when we solve the bracket, sign will get changed. Agree? So 2 minus 1, 1. Okay, 1 by n plus 1 by n, 2 by n. Okay, so now what will I do? I will apply limit. Okay, if n goes to infinity, what will happen if n goes to infinity? 1 is constant, so it will be as it is. If n goes to infinity, 1 upon infinity is 0. So 1 plus 0 is equal to 1 as n tends to infinity. So that means the diameter, that means the length here goes to 1. Therefore, length of Fn goes to 1 as n tends to infinity. But see, we want diameter or the length goes to 0. We are not getting it. So therefore, the fourth condition is not satisfied. Let me mention, therefore, length of Fn does not go to 0 as n tends to infinity. So the fourth condition is not satisfied. Therefore, Cantor's intersection theorem is not applicable. Let me mention here, is not applicable for this sequence of sets Fn. Okay, so not applicable. The first part is over. Now we have to go for the second part. We have to find the intersection. Let me mention here. Now we will find intersection Fn, n belongs to set of natural number. Okay, that intersection we will find. So we have a very common technique. I will take any arbitrary point from the intersection and we will try to find out. Let x belongs to intersection Fn, n belongs to set of natural number. See, x is in intersection, it means x lies in all sets. X belongs to Fn for all n belongs to set of natural number. X belongs to, I will put the definition of Fn here. So it is a closed interval. What we have, 1 minus 1 by n, 2 plus 1 by n. It lies in interval, it means 1 minus 1 by n less than or equal to x less than or equal to 2 plus 1 by n. Okay, so x lies in interval, that means x is greater than or equal to the first point and x is less than or equal to the last point or end point. What will I do? I will apply limit to all sides as n tends to infinity. Therefore, limit n tends to infinity 1 minus 1 by n less than or equal to limit n tends to infinity x less than or equal to limit n tends to infinity 2 plus 1 by n. Okay. See, just make a screenshot of it, then we will go further. So by applying limit, let us see what will I get. 1 is constant, will be as it is. I am applying limit here. 1 upon infinity is 0. So 1 minus 0. X is independent on n. So it will be as it is. Less than or equal to 2 is constant. If you apply the limit, 1 by n will be 0. So that means 1 less than or equal to x less than or equal to 2. That means if you take any point in intersection, you will always get x lies in 1 and 2. Getting? Including 1 and 2 less than or equal to we have. So therefore the intersection of all these sets will be obviously close interval 1 comma 2. Okay, so in this way we found out the intersection of all these sets. The example is over. Just make a screenshot of it, then we will stop. Thank you. See you in next video.